third. Okay, so we will see first some basic concept in linear transformation. Okay, so wait for a minute. Wait a minute. Okay, now look at here. Unit number one, linear transformation. Okay, tell me, what is the linear transformation? Anyone? What is the definition of linear transformation? When we say that the function is linear, anyone knows? Hmm?
The transformation T from vector space U to W is said to be linear if
Hmm?
T of AU plus AU plus BB is equal to A into T of U plus B into T of V, where AB are scalars and V and W are vectors from vector space V and W.
Very good. So what is the definition of linear transformation? Okay. Definition. The linear transformation. Okay, the linear transformation is nothing but let capital V and capital W be a vector space. Okay, over the field F. Over the field capital F. And a linear transformation from a transformation okay, V into W, V into capital W is a function from V into W. Okay, sorry, a linear transformation. A linear transformation V into W is a function from V into capital W such that T of C into alpha plus beta is equal to C into T of alpha plus T of beta, where alpha and beta are belongs to the vector space V and C belongs to capital F. Is it correct?
Yes, sir.
Let V and W be the vector space over the field F. Okay, a linear transformation V into W is the function from V into W such that T of C into alpha plus beta is equal to C into T of alpha plus T of beta. Okay, there is no need to take one scalar here. Okay, C into alpha plus D into beta. It is sufficient for take only one scalar, C into alpha plus beta. Okay, so this is the definition of linear transformation. Now the second definition is null space. What is null space? Suppose this is the vector space V and this is the
Subspace of domain vector space.
subspace of, okay, this is the vector space W, and suppose T is this transformation from V to W. Okay, so it is the subspace of domain. Okay, suppose this is N. It is null space of T. By the definition of null space, what is the definition of null space?
The
Null
vectors in
space.
V which maps to 0 in W.
Okay. Suppose this is the zero vector in W. So take collection of those vectors of V which maps zero vectors to Codomain. ओके, अशी कलेक्शन घ्यायची की हा कुठे मॅप व्हायला पाहिजे, या zero ला map करना पड़ेगा. Okay. So null space of T is nothing but what? Hmm. Collection of those vectors of the domain V such that T of alpha is equal to 0. Okay. So it is the subspace of domain 1. Okay. Now definition what? Let small b, capital B, and capital W be a vector space over the field F, over the field capital F, okay, and let capital T be a linear transformation, a linear transformation V into W, okay. Then the null space of T, okay, is the set of all vectors in hmm, capital V, that is alpha belongs to capital V, such that T of alpha is equal to 0. Okay, if T is linear, so T of 0 is equal to 0. Okay, so 0 always contained in null space of T. ओके एखाद्या सेटमध्ये जर झिरो वेक्टरच नसेल तर तो सबस्पेस होणार नाही. तो सबस्पेस आहे म्हणजे याच्यामध्ये झिरो वेक्टर असायलाच हवा. ओके सो what is the null space? Collection of those vectors in capital V, that is domain, such that T of alpha is equal to 0. Okay, that is T maps to 0 from codomain. Any doubt in this definition?
No, sir.
Now the next definition is range or rank of T. Rank of T. Before going to rank of T, now tell me what is range of T?
The
Range.
subspace of codomain.
Yes, it is a subspace of codomain. Suppose this is the V. This one is W. And T is the linear transformation from V to W. Okay, we don't know that this mapping is onto or not. We don't know this mapping is onto आहे का हे आपल्याला माहित नाही. Okay, so always T of capital V always contained in what? W. If T of V, okay, whole space, vector space V is equal to W, then this T is what? Onto.
Onto.
Okay, and this one is into. Okay, so this one is range of T. So if range of T is the subspace, proper subspace of codomain, then it is into. If range space of range of T is equal to whole codomain, then the function is onto. Okay, so this is T of capital V. So hence range of T is what? Range of capital T is what? Subspace of W. Okay, any doubt?
No, sir.
Right answer. Range of T. Range of T is equal to T of alpha such that alpha for some alpha belongs to capital V. Is it correct?
Yes, sir.
Okay, म्हणजे रेंज ऑफ टी मध्ये तुमचा एलिमेंट कोणत्या टाइपचे असतील? टी ऑफ अल्फा. Okay, now the next definition is rank of T. Rank and nullity of T. Rank of capital T. Okay, Hmm. V is finite dimensional vector space. Okay, FDVS means finite dimensional vector space. Then the rank of T, the rank of capital T, hmm, is the dimension. Okay, is the dimension of the range space of T. Range space of capital T. Okay, we know that. What is range of T? Range of T is equal to T of alpha for some alpha belongs to capital U. Okay, again we know that this is the what? Subspace of W. Subspace means itself it is a vector space first. Okay, जर एखादा वेक्टर स्पेस असेल तर त्याला डायमेन्शन असेल. Okay, and that dimension is nothing but is what? Rank of T. Okay, if V is the finite dimensional vector space, the rank of T is nothing but the dimension of range space of T. Okay, range space is nothing but range space is itself a vector space. Okay, that is the subspace of Codomain. Means itself it is a vector space. Hence, it has a dimension. And that dimension is nothing but rank of T. Okay, and the Similar, similarly, the nullity of T is mean what? Hmm. Dimension of
Dimension of null
null
space.
space. Okay, nullity of T. ओके हा लिनियर अल्जेब्रा खूप इम्पॉर्टंट आहे बरं का लिनियर अल्जेब्रा आणि रिअल अनालिसिस नेटला 120 मार्काचा वेटेज आहे ओके तो नीट लक्ष देऊन ऐका फक्त लिनियर आणि तुम्ही रिअल जरी केला स्टडी तर तुमचं नेट निघू शकतो ओके नेट क्वालिफाय होऊ शकतो फक्त दोनच पेपरचा अभ्यास डीपली करायचा ओके सो व्हॉट इज द नलिटी ऑफ टी इफ V is finite dimensional vector space. If V is finite dimensional vector space, then the nullity of capital T is the dimension of null space of T. Okay. The nullity is what? Dimension of null space of T. Okay, any doubt in this definition?
No, sir.
Okay. Now the next point is rank nullity theorem. Okay. What is rank nullity theorem?
Rank plus nullity is equal to dimension of domain vector space.
Very good. The rank nullity theorem. Okay, let capital V and capital W be a vector space. Let capital V and capital W be the vector space over the field F. The vector space over F, and let capital T be a linear transformation. Linear transformation from V into W. That is T of V is subset of what? W into means. And suppose capital V is what? Finite dimensional vector space. Then, okay, the condition important. Is finite dimensional vector space. Then, the rank of T plus nullity of T is equal to dimension of V. domain V, and this is the transformation T from V to W. Okay, and nullity of T means what? Null space is the subspace of our domain. This is N of T. Okay, this one is what? Range of T. Okay, this nullity of T plus range of T. That means rank of T. The dimension of this space plus dimension of this space is nothing but what? Dimension of our domain. Okay, dimension of our domain. Okay, this is the rank related theorem. Any doubt? Up to here?
No, sir.
Okay. Now the next definition is linear operator. What is linear operator? What is the difference between linear transformation and linear operator? And one more is there, linear function. More concept is there, linear function. Functional analysis झाला ना lecture? Yet.
No, sir. Introduction दिली फक्त.
Introduction. Okay. So linear operator is nothing but our domain and codomain is same. Okay. In the linear transformation, if domain and codomain are both are same, then that linear transformation is nothing but linear operator. And the linear functional means our codomain is field, not a vector space. Okay. First, we will see linear operator. This linear operator. Let capital V be a vector space over the field F, capital F, a linear transformation, a linear transformation T from V to V, okay, into V. It's called linear operator. Okay. On capital. Any doubt? If the domain and
No,
codomain
sir.
are same, then that linear transformation is nothing but linear operator. Okay, त्याच वेक्टर स्पेस मध्ये ऑपरेट होतो. Okay. Now the next definition is linear functional. Linear function. Let capital V be a vector space over the field F. Over the field capital F. A linear transformation. Linear transformation. Take T from, or we can functional denote as a F. We can F. Functional is तो आपण सहसा F लिहितो linear functional is okay. F from V into capital F. Okay, tools field V over F to F. Okay, whatever with the field V over F with the F into. Okay, so F is the function from V over F to F. आणि हा field कसा असायला सेम असायला बरं का. Okay, a linear transformation F from V into capital F. It's called.
सर माझ्या फ्रेंडला जॉईन होता येईल.
ऑटो एडमिट नहीं है ऑप्शन. Wait. Okay. So it's called linear functional. Okay. What is a linear functional? Let V be the vector space, a linear transformation V into capital F. Okay, the V over F. This F and this F must be same. Okay, any doubt in this definition?
No, sir.
Now it is clear what is linear transformation, linear operator, and linear function. Okay. Now look at some examples. First one, show that a function, okay, show that a function small f defined on vector space, defined on vector space Fn, okay, into capital F by f of the input क्या है मतलब the vector with n coordinates, okay, f of x1 x2 up to so on xn, okay. What is vector here? जसं R2 असेल तर काय करतो आपण ऑर्डर्ड टपल, okay. R3 असेल तर ट्रिपलेट. So here Fn, okay, f cross f cross f cross up to n times. So each vector with n coordinate is there. Any doubt?
No, sir.
Okay, so here f of x1 x2 up to so on xn is equal to a1 x1 plus a2 x2 plus up to so on an xn, where this ai belongs to capital F, from I running from 1 to up to so on n. Okay. Now prove that this one is the linear transformation. Is linear functional. काय तुमचं function? F is defined on, okay, Fn with capital F raised to n to F. Here the codomain is
Yeah.
what? F. So this is linear. This is the functional. Okay, we have to show that this is a linear function. Okay, so we have to prove that the condition of linear transformation, that is T of f of C alpha plus beta is equal to C into f of alpha plus f beta. Okay, look at the proof. We have given, we have f is the function fn to capital F defined by f of x1 x2 up to so on xn, which is equal to a1 x1 plus a2 x2 plus up to so on an xn, with where each ai belongs to capital F. Okay, now to prove that f small f is a linear functional, we have to prove that the f is linear functional. So let take two elements from Fn, that x and y belongs to f raised to n and c belongs to capital F, be any scalar. Okay, these are the two vectors and c is the any scalar. Okay, so What is the form of x? Where x is equal to x1, x2 up to so on xn. What is the form of y?
y1, y2 up to so on
y1,
yn.
y2 up to so on y. Okay, now consider f of cx plus y is equal to f of c into x is x1, x2 up to so on xn plus y1, y2 up to so on yn, which is equal to f of cx1, cx2 up to so on cxn. Okay, plus this y1, y2 up to so on yn, which is equal to f of cx1 plus y1. Okay, coordinate wise addition cx2 plus y2 up to so on cxn plus yn. Okay, is it correct?
Yes, sir.
Now, by the definition of what? f f of x1, x2 up to so on xn is it equal to what? a1, x1, a2, x2 plus up to so on an xn. So, by the definition of f, small f, this is equal to what? f of cx plus y is equal to a1 cx1 plus y1 plus a2 cx2 plus y2 up to so on an cxn plus yn. Okay, where each ai belongs to capital F. Any doubt up to here?
No,
Any
sir.
doubt up to? Okay. This is equal to a1 c x1 a1 y1 plus a2 c x2 plus a2 y2 plus up to so on an cxn plus an yn, which is equal to now take c common. This one is ax1 plus take c common from this one ax1 plus ax2 plus up to so on what an wait a1 this is a2 this is an xn. Is it correct?
Yes, sir.
Plus another bracket a1 y1 plus a2 y2 plus up to so on an y. Okay, now this is equal to c into by the definition of f, this is nothing but what f of
x1, comma x2,
x1
comma up to so on xn.
xn. Okay, plus this is f of y1 y2 up to so on yn. Okay, so this is f of cx plus y is equal to c into this is f of this one is x plus f of y. Hence, the given function f is what? Linear functional. Any doubt?
No, sir.
Okay. So that the function f defined on fn into f by f of x1, x2 up to so on xn is equal to a1, x1, a2, x2 up to so on an xn, where each ai belongs to f is a linear function. Okay. Now the second one is second example. Let n be the positive integer. n be a positive integer, and f of n cross n be the set of all n cross n matrices. Be the set of subset of right down vector space. Vector space of all n cross n matrices. Okay, over the field capital F. Then show that the mapping is given by T from f n cross n, f raised to n cross n to the f is a linear linear functional such that trace of a, okay, defined by trace of a is equal to what? What is trace of a?
Addition of diagonal elements.
Okay, additional diagonal elements, that is a11 plus a22 plus a33 up to so on a n n. Okay, trace of a, trace of a. This one. If suppose a is, if the matrix A is like this, a11, a12 up to so on a1n, a21, a22 up to so on a2n. This is an1, an2 up to so on an. Then the trace of is nothing but what? All the addition of these diagonal elements. Okay, so trace of A is nothing but a11, a12 up to so on a1n. Okay, this a11, a22, all the entries of A is from F. So this addition also belongs to F. Okay, hence the trace of A, the output belongs to the field F, and hence it is the linear function. Okay, first we have to show that the condition of linearity. Okay, understood what is a trace of A? Any doubt?
Yes.
Okay, now we have to show that this function is linear function. Answer. We have start writing here T, write down TR, that is trace function. Okay, we have TR from Fn cross n to F by trace of A. ओके, याच्यातला प्रत्येक वेक्टर म्हणजे तुमचा काय असेल, एक मॅट्रिक्स असेल बरं का, ऑफ ऑर्डर n क्रॉस n. So here the matrix A, the trace of A is equal to what is given to us, 1 1 a11 plus a12 plus up to so on a22 a n. Okay, any doubt?
No, sir.
Okay, now since A belongs to what? F raised to n cross n. Okay, and A is nothing but what? The matrix Aij of order n cross n. And we have to prove that this function TR is linear functional. Okay, so we have to prove that this TR is a linear function. So let take two matrices from the our domain. Let A is the matrix such that Aij of order n cross n, and B is the matrix Bij of order n cross n. Be any elements or any vectors of f raised to n cross n, and take C be the any element of the field f. It is scalar. Any scalar. Okay. Consider dr of C into capital A plus B is equal to what is A? This is dr. C into what is A here? Aij of order n cross n plus Bij order n cross n, which is equal to trace of A plus B is equal to what? Trace of A plus trace of B. Is it correct?
Yes, sir.
Okay. So this one is trace of C into Aij plus Eij. Okay. So writing this Aij plus Bij. What is the order of this one? N plus n. Okay. Which is equal to now the trace of this one is equal to what? C into A11 plus B11. Okay, plus again C into A22 plus B22. Is it correct? What is C into A? C into A11, C into A12, up to so on C into A1n, up to so on C into A n1, up to so on C into A n. What is the trace of C into A? Is it correct?
C into A11.
हा तुमचा झाला CA प्लस B काय येईल? CA11 प्लस B11. इज करेक्ट. तसंच हा काय येईल शेवटचा डायगोनल एलिमेंट C into ANN plus BNN. Is it correct?
Yes, sir.
Okay, हा असा मॅट्रिक्स आहे तुमचा. C into A plus B. C into A plus B. Okay, now trace of C into A plus B is nothing but C into A11. Wait. C into A11 plus B11 असा आहे.
कंप्लीट ब्रॅकेट नाही येणार सर.
कंप्लीट ब्रॅकेट नाही. वेट. ओके, इथे ब्रॅकेट नाही. C into A11 plus B11. Okay, plus totally bracket plus C into A22 plus B22. Okay, plus now it is correct. C into
Yes, sir.
ANN plus BNN. Okay, so this is what trace of C into A plus B. Okay, now take C common from this one. C into A11 plus A22 plus up to so on plus ANN plus another bracket B11 plus B22 plus up to so on BNN, and this one is T into this is what trace of capital A plus this one is trace of capital B. Okay, hence trace of C into capital A plus B, capital B is equal to C into trace of A plus trace of B. Okay, hence from the condition of linearity, hence this function is what? Linear function. The trace of trace is the trace function is linear function. Any doubt?
No, sir.
Okay, these are the some basic concept and some basics examples. Okay, now we will see the next definition is dual space. What is that? Dual and double dual, and some theorems on it. Okay, any doubt up to here?
No, sir.
No, sir.
Next definition is dual space. शिकलाय ना dual space V star BSc ला. Hmm? Anyone knows what is dual space? I का माहित का नाही?
No, sir.
The collection of all linear all linear functionals on a vector space V over F. Okay, it's nothing but dual space, and it is denoted by V star. Okay, the collection of all linear functional on the vector space V over F. Okay, and it is denoted by V star or LVF. It's denoted by V star or LVF. That means collection of those linear functionals on V. Okay, मेरे तुमचा कोडोमन काय असेल? Or the collection of those vector linear transformation or linear functional on vector space V over F. Okay, so L of V, LVF, it's called dual space. Dual space of capital V. Okay, and it's denoted by V star or LVF. Okay, what is dual space? The collection of all linear functions. Functional space, our codomain is must be a field. Okay, the collection of all linear functionals on the vector space V over F is called as dual space of V, and it is denoted by V star or LVF. Okay, म्हणजे हा सेट कसा असेल तुमचा LVF is equal to collection of T. Okay, collection of all linear functions T such that T is the functional from V over F to yeah, which is yeah. Okay, set of all linear functional over the vector space V over F. आता फंक्शनल म्हटल्यानंतर फ्रॉम एफ टू एफ म्हणायची गरज नाही आहे. एकदा फंक्शनल म्हटल्यानंतर तुमचा कोडोमेन हा फील्डच असणार. ओके, आणि हा ड्युअल स्पेस तयार करतो सर. ओके, स्पेस इटसेल्फ हा वेक्टर स्पेस तयार करतो. ओके, होम एच व्ही असं लिहिलं की नाही काय? होम व्ही डब्ल्यू बी एस झालं की नाही?
No, sir.
नाही झालंय. लिनियर अल्जेब्रा
Dual space नाही झालं, sir.
नाही. होम एच व्ही होम व्ही डब्ल्यू झाला की नाही? Collection of all the vector linear transformation from V to W is called as home VW. Linear होता ना BSc ला?
Yes, sir.
Yes, sir.
Okay, dual space is nothing but collection of those linear functional on the vector space V over F, and it forms itself a vector space. That's why it is called as dual space. It is a space. A space तयार होते. Okay, कोणतं ऑपरेशन आहे कॉम्पोजिशन ऑपरेशन नुसार तो हा itself हा वेक्टर स्पेस तयार होतो. ओके, आता डबल ड्युएल पण आहे त्याच्यावर. ओके, ते पुढे पुढे नंतर केल्यानंतर येईल का. ओके, एनी डाऊट अप टू हियर.
No, sir.
Okay, look at here once again. What we studying up here? Definition of linear transformation. Okay, T of C into alpha plus beta is equal to C into T of alpha plus T of beta. Alpha beta belongs to B and C belongs to F. What is null space of T? Collection of those vectors of codomain such that it maps to zero vector of our codomain. And range of T is nothing but what? Range of T is equal to T of alpha for some alpha belongs to capital V. If T of alpha and T of V, capital V, is contained in, properly contained in, properly contained. If it is properly contained in W, then its function is onto. If T of V is equal to W, then its function is onto. Okay, what is range of T? Range of T itself forms a subspace of our codomain, and the dimension of that subspace is nothing but rank of T. What is nullity of T? Nullity of T is nothing but dimension of null space of T. The rank of T is nothing but nullity of T is nothing but dimension of null space of T. Rank nullity theorem is rank of T plus nullity of T is equal to dimension of our domain. Okay, domain लक्षात ठेवायचं. काही वेळेस काय करतात, T फ्रॉम W टू V देतात, असंही देतात फंक्शन. आपण हे पाठ केलेलं असतं त्यामुळे मग ते घोळण्याची शक्यता असते. Rank of T plus nullity of T is equal to dimension of our domain. Okay, here the dimension of domain is nothing but dimension of V. What is linear operator? If the domain and codomain if same, then that linear transformation is nothing but linear operator. If the codomain is if the codomain is function, then the linear transformation is linear functional. Okay, any doubt in this example?
No, sir.
Okay, from tomorrow we will see the theorems. Okay, right, look at this one here. On this statement we will see the proof, we will see on the next lecture. Look at it here. Let capital V be an n-dimensional vector space over the field capital F. Okay, I have इथून पुढच्या प्रत्येक थेरमला हा स्टेटमेंट फिक्स आहे. Okay, n dimensional किंवा finite dimensional over the field F. V be the n finite dimensional vector space over the field F. The statement fix असेल. Let V be an n-dimensional vector space over the field F, and let the beta is equal to the set beta is equal to alpha 1, alpha 2 up to so on alpha n be any ordered basis. Wait. Any ordered basis. Any ordered basis of capital V. Okay, wait. Wait a minute. Okay. Okay. Alpha 1, alpha 2 to so on alpha n be any ordered basis of V, then there exists a unique linear functional. There exists a unique linear functional F on capital V such that capital V such that f of alpha I is equal to xi, where I running from 1 to up to so on. काय सांगितलंय V हा एक तुम्हाला वेक्टर स्पेस दिलेला आहे आणि बीटा तुमचा ऑर्डर्ड बेसिस. Okay, any ordered basis. You know that the basis is not unique for any vector space. Okay, so this one is any ordered basis of V, then there exists a unique linear functional. Okay, so functional म्हणजे काय हा f कुठून असायला हवा तुमचा V to capital F. Okay, this there exists a unique linear functional f such that f of x alpha is equal to x for I running from 1, 2, 3 up to so on. And what is the meaning of this sentence? F of alpha is equal to xi is nothing but what? F of alpha 1 is equal to x1. F of alpha 2 is equal to x2. F of alpha 3 is equal to x3 up to so on. F of alpha n is equal to xn. म्हणजेच काय, हा जर तुमचा x1 x2 जर डिफरंट असेल तर हा अल्फा 1 अल्फा 2 जर डिफरंट असेल, if alpha 1 alpha 2 is different, then x1 and x2 also different. That means the image of each and every alpha I is different. Okay, the f of alpha 1 is not equal to f of alpha 2. Correct?
Yes, sir.
कळते का काय सांगतो, याचा अर्थ काय, f of alpha is equal to xi for I running from for all I running from 1 to up to so on n. It means that if alpha 1 and alpha 2 are different, their image is also different.
Means 1 correspondence, ma'am, sir.
correspondence ओके, हा फंक्शन असा एक तरी फंक्शन एक्झिस्ट होईल जो 1 1 correspondence असेल. ओके,
Yes, sir.
proof we will see in the next lecture. Okay, for today it is sufficient. Any doubt in this lecture?
No, sir.
No, sir.
Okay, so thank you for the attending the lecture. Okay, the remaining part we will see tomorrow. Okay, you can leave now. Thank you.